Okay, so this is another problem on KSP, solubility product. This time they are talking about what range of pH will be a selective precipitation. And so this is a case where it's copper 2 plus, and the copper 2 plus gives in a form of 0.1 molar concentration. Also, the mangan, which is a mangan 2 plus, I think that there's a typo here, mangan 2 plus, that's the same concentration. So I think most of you already know, but let me give you a short overview. What do you mean by pH? And so this is a concept about pH. Typically pH 7, I think you remember your neutral, and this is when you have a low number such as 1. Even it's possible to have an even smaller number than 1, but it's typical ranges in this range. And then that's the one that where we call acidic. This is more basic or alkaline, and that means H plus concentration is high, and that means OH minus concentration is low, right? And also that means high OH minus concentration, low H plus concentration. And you can use a value of pH, and this is a number 7 is the typical breakpoint, but it's the pH scale trying to relate either concentration or H plus. And so there is also another relationship, which is pH is something that minus log 10 to the H plus. So does POH is minus log 10 to the OH minus. At room temperature, the pH plus POH is 14. That's the nature of the water, and this will be a sort of the basic concept. And then the range of the precipitation, what pH will form, and we need to essentially calculate the value Q, as we discussed before. When Q is bigger than KSP, precipitation will happen. If the Q is smaller than KSP, no precipitation. Okay, so those are the overview in this problem. Okay, so let's solve this problem one by one. And so let's go with this first one. So first one is just okay. So we're talking about mangan, right? So Mn2 is Mn2 plus 2 times OH minus. So therefore, the Q is Mn2 plus and OH minus square. And then we need to find out what's the value. And as you see here, 0.10 molar concentration. And OH minus concentration is something that we do not know. So we want to find out. And then this is when this one becomes same as a KSP, which is a 1.6 10 to the minus 13 precipitation. That's a precipitation point, right? And then we can establish the ranges a little bit later. So naturally, this equation is, I think, is instinct is better to calculate POH first, and then we can calculate the pH later, right? So so this POH is coming from knowing OH minus concentration. Okay, so what's my OH minus concentration in this problem? OH minus square is 1.6 10 to the minus 13 times 10 to the, I guess, the 1. So that's 1.6, 10 to the minus 12. Therefore, OH minus is square root 1.6, and this becomes 10 to the minus 6. And then I will have that number, which is about 1.3, 10 to the minus 6 molar. Okay, I got that. And then I can calculate POH, which is based on minus log 10 OH minus. And so therefore it is plus 5.9. Then makes it pH is 14 minus 5.9. And then make it 8.1. Okay, so that's what is called the precipitation point. And then I wanted to explain this situation in a more graphical manner because I think about this situation. Right? So let's see. I'm gonna draw the pH here, and then we know the value of 8.1 pH will be the precipitation point. And this is means OH minus concentration is high, right? And this is OH minus concentration is low. And the pH scale is because negative log 10 H plus, it is the H plus is high and H plus is low. But what is that? I think the useful here is to use an information about when you have a sufficiently large high concentration, this is where we are seeing precipitation. So that's the precipitation ranges. When your pH is higher than 8.1, you will see the precipitation. So let me just graphically show that. And that's the case of MnOH2 in this case. And so now, okay, so, well, I can do the same thing for the problem set showing in the second problem, 2, which is now copper OH2, the same as copper 2 plus, 2 times OH minus. So math is almost same here. So Q is copper 2 plus OH minus to the square, and that's a 0.10 molar because that's the one shown up here, and then multiply by OH minus to the square. That's the concentration we're going to figure out, and when this Q is same as KSP, 4.8 10 to the minus 20 is what is called, once again, is that's a precipitation point. So let's calculate the critical OH minus concentration where precipitation starts to occur. So that should be square root 4.8 10 to minus 19. And that will lead me to 6.9 if you plug in your calculator, and 10 to the minus 10 molar. And if you calculate POH, the value is 9.2. So therefore, the pH, which is 14 minus POH, is 4.8. So I am going to draw once again. This is a pH and 4.8, and 4.8 higher. This is where you have OH minus concentration is high enough. When you see this concentration is high, you have sufficiently higher concentration that will drive this one to form this precipitation, right? So therefore that means a copper OH minus 2 precipitation will happen, right? So that's my hash line. Okay, so having said this, combining these two will naturally comes to the 1 and 2 together. Let me have this diagram here. Once again, this is a pH ranges, and then we know 8.1 and higher pH precipitation of, what was the compound? Mangan OH2 will happen. Same pH scale, 4.8 and higher. That's the ranges of pHs where you will see copper oxide precipitation will happen. So now we find these regions of our interest, which is, and this is a range of pH, which is a 4.8 between 4.8 and 8.1. We will see, so pH 4.8 between 4.8 and 8.1. No precipitate of MnOH2, but PPT precipitation of copper hydroxide. Okay, so that's the answer for the ranges, because what was the problem was, okay, what range of pH would permit selective precipitation of copper as a copper hydroxide? Yeah, as you can see that this is a range, in this range, that's the ranges where we are seeing the selective precipitation of copper. Okay, so that's the answer for this. Thank you.